Hi everyone. My name is Rajesh Vayavur. I'm currently working as a research associate for geophysics, especially for potential field modeling and inversion. So for this talk, I'm going to present 3D integration of geological and geophysical datasets of Eastern Sudbury Basin. So the main takeaway from this talk will be how can you see like different geophysical and data sets can complement each other and then can provide a comprehensive subsurface interpretation. So this is the research team working on this project. So we have geophysics geologist Rasmus, MT, Edamola, Saeed, Mustafa, Richard, John, Ross from Metalith side, and then from company side, Valen, Glencore side, Kevin, Lisa, Enrique, Warren, Guido. And then basically my roles and responsibilities for this project is to perform 3D potential field modeling and inversion, and also to coordinate with the different team members to for 3D integration of various geological and geophysical data sets, and to build a robust 3D geological model of Eastern Sudbury Basin. So coming to the some partners, like we have partners from software partners from Mira Geoscience, Emerson, Sequent, and Esri, and then industry partners are Valiant, Glencore, and then government organization. So this outline of my talk. I'll start with the background and then give a historical perspective of the Sudbury Basin. And then I will talk about the geological background and various geophysical data sets we used for this study. And then I also do some like 3D integrated analysis for an interpretation, and then finally summary and findings. So our study area located in the southern Ontario. So this is a Metalith TRANSECT map. So you can see the Sudbury is located in the somewhere here. So coming to the historical perspective of the Sudbury Basin, so we all know the Sudbury Basin is basically world class, famous for world class deposits, especially nickel, copper, cobalt, and PG deposits. And most of the deposits occur along the rim of the Sudbury Basin. So they call as Sudbury Igneous Complex. And then in the eastern part of the Sudbury Basin, there are like not very economically viable deposits, especially in the eastern part of the Sudbury Basin. So in order to find more targets and identify deposits, Metalith, in collaboration with Valiant Glencore companies, taken a research initiative to look into the eastern part of the Sudbury Basin. So this is the study area I'm working on, eastern part of the Sudbury Basin. So basically the geology, this is a simplified geology map after Monchon et al. In 2018. So we all know that this Sudbury structure formed because of large meteorite impact at around 1.87 billion years ago. And the current structure lies towards north on Archean granitites and gneiss rocks, and towards the south on Paleoproterozoic Huronian sedimentary rocks. So after the impact, like Sudbury structure undergone a lot of deformation, especially I am highlighting two important main events like South Range Shear Zone and then Grand Valley Front tectonic zones to the south. So what are the possible research outcomes from this project? So we are trying to interpret the upper crustal architecture of the eastern part of the Sudbury impact structure, and then to identify new targets of potential zones of mineralization, and finally to build a 3D geological model of the upper crust 10 kilometers of Eastern Sudbury Basin. And this model can be used, like this kind of study can be used in other similar ore deposit models worldwide. So these are possible general future, like general outcomes in terms of like we can guide exploration companies for exploration of new deposits and develop mines, and then net zero emission and economic development. So coming to the data sets we have for this study, this is the TRANSECT we are working on. So we have seismic data, both the regional and high resolution seismic data sets, and then MT and audio AMT data sets, and then gravity data, So we acquired all these data sets, and we also using publicly available data sets, aromatic grids, and then mineral occurrence database from OGS, and then we are using Valley provided 3D COCAD model for top 5 kilometers of the Eastern Sudbury Basin. So we performed, so we are carried out several geophysical ignition, especially in 3D. So at different scales. So this is the AMT inversion, and then these are broadband magnetotelluric inversion study, and then there's a gravity magnetic inversion outline. So there are like a lot of time and effort put into it, especially in inverting this AMT and BBNT models. So I would like to acknowledge Eddie for providing me the AMT and BBNT models for this studies. So we'll start with AMT model. So we have this high resolution data set from companies provided by Valley and Greencore. So we are using that data set for inverting the data set, and then this is a final inverted model. So these are the data locations on the AMT model. So this is a code used ModEM code for inverting this AMT dataset. So we took isosurfaces from that AMT model. So basically we used 1 to 100 ohm meters iso volume. So these are the C1, C2, and C3 conductors we identified from that AMT model. So based on the density, like high density of the data set, we can say C1 and C3 are like high confidence conductors, and C2, since it's there is not enough data there, you can like say moderately to high confidence connectors. So what are the research questions for this study? So how these connectors are emplaced here, and then is there any deeper sources connecting to these connectors, and what are the structural controls on these connectors? So for that, we started with the potential field modeling and inversion. So this is a gravity data set we used. So this is the TRANSECT, Middle-earth gravity TRANSECT, and then we are using GSC gravity data set around the TRANSECT. So we combine, so we process the data, and then this is the final complete Boger anomaly grade. So we can see a reduction in the gravity field, especially in the eastern part of the Sudbury Basin. So this is a final density model after inverting the gravity data set. So we used a BPMG algorithm taught by Fullecker. This is a final RMS misfit for this is 1 millicol. So this is a total magnetic intensity grid we used from OGS database. So again, you can see the reaction in the magnetic field in the eastern part of the Sudbury Basin. So we'll investigate all these things in our presentation. So this is a final susceptibility model after inverting the magnetic data set. So again, we are using BPMG algorithm for that. So we are actually taking a cross section from the density model. So you can see clearly the smooth variation of the densities in the subsurface. So yellow, the blue ones are low densities, and the high ones are like high densities, like red ones are high densities. So if you overlay the geology map on top of that, so you can see so the Sudbury Basin is nicely clearly delineated here, and then the Paleoproterozoic metasediments is coming up nicely here, and then there is a high density zone from Grand Relief Front tectonic zone, and we are also picking up some high densities in the subsurface. So we will investigate those features also. So basically, this is a smooth inversion. So we all know that gravity and magnetic smooth inversions are will be having a non-uniqueness problem. So for a single dataset, you can generate multiple models. So how do you validate this model? So we will start. So we'll collaborate with other geophysical evidence. So here I'm actually overlaying the Valley provided 3D model surface. This is a borehole constraint surface. So I overlaid here on top of that 3D cross section. And then you see the 2D projection there. The dips of this cross section matches with the 3D inversion cross section. So we are slightly confident about the model. So we can still corroborate with other geophysical evidence. For example, so first so we will interpret the density model as it is. So you can see I'm interpreting a deep-seated faults here. Especially you can see a gradient in the density model. So I interpret a deep-seated fault. So I'm interpreting a thrusted block here, and then this is a base of SIC. So we compared that model with the pre-existing model. So this is Olanian performed in 2015. He taken lithoprobe data and then used 2.5D modeling to image the entire Sudbury structure. So we are comparing that thing with our model. So we are comparing this cross section here. So this is 2.5D modeling, and this is the 3D inversion cross section. So you can see nice correlations, especially so the thrusted block here. You can see there's a thrust block here, and then the entire Sudbury basin. It's smooth variation of Sudbury basin, and then the Huronian sediments is coming up here nicely. But we are picking from the 3D inversion also the deep-seated fault here, like in 2.5D modeling. They are not able to distinguish between there's no variation here, but in the 3D inversion you can pick that variation nicely. So we'll also investigate this high densities from this model. So in the next slides. So basically, if you see this thrusted block, and then I took an isosurface of this thing, and then if you see this thrusted block in 3D, so it's basically you can trace that fault. So these Sudbury basin trough represents the Sudbury basin, and then this a trough represents the Huronian group of sediments. So I overlaid the isosurface surface from Vallée-Gocard model and the conductivity anomalies. You can clearly see that it nicely sits in the surface. So this is the cross-section view of the conductive anomalies. Again, if you see, we interpreted the deep-seated fault, and this conductive anomaly is proximal to this deep-seated faults, and this conductive anomaly is proximal to this deep-seated fault. So again, like if you overlay the Vallée-Gocard model, you can see it's cross-cuts that anomaly, conductive anomaly. So it may be like contact or footfall type of deposit. So basically, we are trying to investigate this deeper features. So we took isosurfaces of these features, and then you can see these isosurfaces. You can clearly see there is a folding kind of feature of the high dense anomalies. And also we overlaid isosurfaces from magnetic susceptibility model. So we can clearly see that there is a discontinuity in between this D1 and D2 anomalies. So we interpreted a deep-seated fault. So this faults here matches with the cross section here. This faults. So and also we are interpreting a deep-seated fault because of the discontinuity in the S1 and S2 features. So I will, if you see from the top view of the same model, now you can clearly see that there is a SZ zone, like South Range shear zone coming along this direction. So which might displace this high dense anomaly to the eastern side. So we are interpreting like deep-seated faulting and folding features. So this might have deformed the rocks, and then you can see the reduction in the magnetic and gravity fields especially in the eastern part of the Sudbury basin. So Clark et al. Also like based on paleomagnetic data, they found folding features here, so which confirms our models. So we have borehole constrained surfaces from Valley. So we overlaid our conductive anomalies on the borehole constrained surfaces. So you can see the C1 connector sits at the basal contact, and the C2 in the whitewater group sediments, and the C3 at the basal contact of the South Range. So now if you put everything together, now you can see clearly see like you are developing like a 3D geological model of the basin. So the top few kilometers are constrained by borehole data constrained surfaces, and then deeper features are constrained by gravity and magnetic models. So we have all the seismic data along this TRANSECT. So I'm basically concentrating on line 211 and line 182 for this study. So if you see that line 211 and line 182, so you can clearly see them some high amplitude reflections here and here, and then steeply reflections here, and then there is a high amplitude reflections here. So these are high size processed seismic data we got from BASIN company. So I overlaid the density model on top of that seismic data. So now you can clearly see the deep-seated faults we are interpreted from the density model matches with this truncation of reflections here. And the steeply decaying features, if you see here, you will think that it will be like out of plane reflections, but if you overlay the density model, you can see there is some this features may be represent of this trusted block thing. So it may be a out of plane, or it may be the geologically related steeply different reflections. So if I overlay that connectivity anomalies, you can see it nicely sits with the high amplitude reflections, and then this connector sits at the basal contact of. So there is also high amplitude reflections here. So now we establish the deep-seated faults. Now we want to see if there is any correlation with the BBMT model, like broadband MT model. So we inputted the broadband MT model into the study area, and then you can see deep conductive features actually at the same exact location of the fault we interpreted. So we can see similar features like IOCG Olympic Dam features here in the southern range, especially. So this might these faults may act as a conduits for this deep connected features as a fluid flow path for this deep connected features to the shallow connectors features. So if I put this connective features in the 3D model, you can see it nicely sits below the shallow connectors here. So now we can see like a comprehensive 3D geological model of the Eastern Sudbury Basin. So what are the findings? So we had good correlation between various geophysical models and geological datasets. We identified 3 AMT connectors, and then we also identified RC and RC2 regional connectors from BBMT model. And then from potential field inversions, we are basically providing evidence for folding and faulting of mafic and ultramafic rocks, and high resolution images also support this deep-seated faulting. And then we are interpreting this deep-seated faulting could have acted as a conduit for hydrothermal fluid flow. So some of the results were presented at CSCG conference, and then the 2 scientific publications coming on this way. And then recommendations the future recommendation is basically we can still constrain this surfaces using the seismic data, and also you can build a constrained 3D potential geological model using potential field modeling. That's the future work. And I acknowledge all these people like high size for providing data sets, and then Medalit team for helpful discussions, and Pura and Bernia for GS support. And these are the references, and that's it. Thank you.